Hi, this is the MOSOMIC MEMS microphone guide. In this episode we'll go through the factors that determine the value of a MEMS microphone. We'll go through each factor fairly briefly in this one and we'll go into much more detail in later episodes. So this is what we'll be talking about. The key performance indicators versus key value indicators, performance factors such as noise, frequency response, distortion and so on, and also the accuracy and stability of microphones, as well as the importance of robustness and reliability. Stay tuned! This series is sponsored by Innovating Technologies. Hi, I'm Mikko Suvanto from MOSOMIC. Key performance indicators, KPIs, are the factors that determine the performance level of a MEMS microphone. Performance parameters such as signal-to-noise ratio, frequency response and distortion are very important and they often get the most attention when people talk about microphones. Unfortunately, it's a bit too easy to forget that it's not just the performance and features of a microphone that determine its value to someone designing and manufacturing a device. For a device manufacturer or designer, the value of a microphone is zero or even negative if the microphone malfunctions or experiences disturbances or changes its characteristics in a way that, for example, prevents an algorithm from working or makes a disappointed customer return the device to the retailer. The requirements for microphone accuracy and stability have increased, especially in multi-microphone systems. Algorithms interpret extremely small changes and differences in the outputs of several microphones that pick up slightly different versions of the same acoustic signals, so the microphones have to be very accurate. Key performance parameters alone don't address the quality and reliability needs of a device designer or a device manufacturer well enough. To indicate the actual lifetime value of a microphone, we have to include also quality, reliability, accuracy, and stability in the list of key parameters. That's why I've expanded the term from key performance indicator to key value indicator, KVI. In this episode we'll take a brief look at the KVIs. We'll get to a more in-depth description in later episodes. When shifting from key performance indicators to key value indicators, we have to add a few things on the list. The first one is electrical robustness. It describes the immunity of the microphone to radio frequency disturbances, power supply noise, ESD, and other reasonable disturbance factors in the electrical operating environment. The next one is mechanical robustness. It describes the microphone's ability to withstand reasonable mechanical handling and abuse without malfunctioning or changes in the behavior or disturbances in the output. Environmental robustness describes immunity to environmental factors such as moisture, temperature changes, dust, and in some cases, liquids. Short-term accuracy is needed to ensure that there are no changes in the characteristics or performance of the microphone and no disturbances in the output as a result of use case related factors such as changes in temperature, humidity or air pressure pulses, mechanical forces and deformations, light exposure, and so on. The disturbances to be avoided can be, for example, sensitivity changes, noise, or glitches. A good long-term accuracy of a microphone means that there are no changes in characteristics or performance over the lifetime of the component in the device. Okay, let's go to my list of 18 MEMS microphone key value indicators. Like I said, in this episode we'll go through them fairly briefly. A closer look at each parameter will be done in later episodes. Let's go through them one by one. Sensitivity describes the efficiency of a microphone to convert sound into an electrical output signal. For analog output microphones, the unit of sensitivity is dBV, decibels in relation to 1 volt, or volts per pascal. For digital microphones, the unit is dBFS, decibels in relation to the full-scale digital signal. The polarity of a microphone tells us whether or not the polarities of the incoming sound signal and the electrical output signal match. A microphone is either non-inverting or inverting. Directivity is the sensitivity of a microphone as a function of direction of the incoming sound in relation to the microphone. It's described with a polar plot that shows the sensitivity of the microphone from all directions in a horizontal plane. In other words, a polar plot shows the sensitivity in decibels for each horizontal direction from 0 to 360 degrees. A microphone can also be said to be simply either omnidirectional or directional. Omnidirectional means that the microphone is equally sensitive to sounds coming from all directions. Phase is the delay experienced by a signal that passes through a microphone. The unit is degree or radian. This means that phase delay depends on frequency, so it's not a fixed time delay, like latency. The illustration here shows a signal and below the same signal, the phase of which has shifted 90 degrees. Phase response shows the phase shift of the microphone as a function of frequency. The unit is degree or radian. It's plotted with frequency on the x-axis and phase shift on the y-axis. Sound quality and accuracy suffer if the time delays are different for different frequencies. This is called phase distortion. To avoid phase distortion, phase response should be linear. Group delay gives a transit time of a signal through a microphone versus frequency. Group delay is a fixed time delay, and the unit is seconds. It's plotted with the sound frequency on the x-axis and the delay time through the microphone on the y-axis. To avoid phase distortion, the group delay should be flat. This can be achieved when phase response is linear. Frequency response shows the sensitivity of the microphone across the frequency range. It's plotted with the sound frequency on the x-axis and the sensitivity on the y-axis. Typically, the audio range from 20 Hz to 20 kHz is shown. Signal-to-noise ratio, SNR, is the ratio of the self-noise of the microphone and the wanted signal that the microphone captures. Self-noise is the noise generated by the microphone itself in the absence of any sound input. The unit of SNR is decibel. Total harmonic distortion, THD, gives the amount of distortion in the output signal of the microphone. It's the ratio of distortion energy versus the energy of the original signal. The unit is percent. The test input sound pressure level should be specified together with the distortion level. Okay, we have reached the halfway point on our list. We'll continue with a couple more distortion-related parameters. Acoustic overload point, AOP, describes the distortion performance of a microphone at high sound pressure levels. It's the sound pressure level point at which total harmonic distortion exceeds 10%. The unit is dB/SPL. Dynamic range is the range from the lowest to the highest signal level that the microphone can handle. The bookends for dynamic range are typically the acoustic overload point and the self-noise of the microphone. The unit is decibel. Current consumption gives the amount of electrical current a microphone draws when turned on. The unit is ampere. Current consumption is especially important in small portable devices with small batteries. The value of high performance can be degraded significantly if performance is not consistent. Matching from microphone to microphone and the stability of one microphone's characteristics over time, environment, and use cases can be measured and given in many different ways. We'll get into more details in another episode. Power supply rejection, PSR, and power supply rejection ratio, PSRR, describe the microphone's immunity to disturbances in its power supply input. The unit for PSR is dBV or dBFS, decibels in relation to 1 volt or the full-scale digital signal. Both of these values are A-weighted, which means that the measurement results have been weighted to take into account how sensitive the human ear is to disturbances at different frequencies. The unit for power supply rejection ratio is decibel. RF immunity describes how well a microphone is able to reject radiated or conducted radio frequency disturbances. There are various ways to test and specify RF immunity. ESD immunity describes the microphone's ability to withstand electrostatic discharges without malfunctioning. Also, ESD immunity can be tested and specified in various ways. Mechanical and environmental robustness describe the long-term ability of a microphone to withstand all the conditions and abuse it faces in the device when used in real-world conditions. Okay, that was my list of key value indicators. Here's a quick look at the whole list once more. This was just an overview to give you an idea of what's coming. I'll go through each item on this list in more detail in later episodes of this guide. I hope I'll see you around. Cheers! If you have any comments or questions, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you liked what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation.